This is the second lecture of week 12. And here we will study, and further we will study how to solve systems of linear differential equations. And first of all, let me show you some special type of systems which we are mostly concentrated on. And this system is called system in a normal form. So normal form is the following form, and this bold x is a vector here, and this A is a matrix, and this x prime, this is a vector which consists of derivative. And let me show you which system can be written in this normal form. For example, system like you see here. On the left side you see only derivatives here, and on the right side you see only the functions x1, x2, can be x3 and x4. So now the vector x, this bold x, will be the vector of 4 components, and then the vector x bold prime will be the vector of the derivatives. Sometimes for simplicity it's also can be written as x1, x2, x3, x4 prime, also this way of writing as possible. And let me show you how we can write this system, this example, in normal form. So on the left side you see this vector x prime, and this part on the right hand side, this is some matrix A times the bold x. So we need to find what the matrix A is. And the matrix A, of course, consists of the coefficients of the functions. So the first row of the matrix A is just you look at the first equation and you list the coefficients of x1, x2, x3 and x4. So x1 is 2, x2 is t squared. We don't have x3 here, so it means that the coefficient is 0. And the coefficient of x4 is this function. The second line of the matrix, you go to the second equation and again you list the coefficients. The coefficient of x1 is not here, so it must be 0. For x2 this is sine t, x3 is cosine t, and x4 we don't have it here, so 0 again. For the third line here we look at the third equation and we list the coefficients again, so this is all coefficients are just ones. And for the fourth row of the matrix we look at the fourth equation, so we have just 0, so all coefficients are zeros. So we have to write zeros everywhere. So now we may say that this system is in this form where this vector x, this vector which consists of 4 components, and the matrix A is given by this matrix here. Let me show you when we can write something in normal form. It's not, in fact, only for systems, it's also for differential equations. For example, let's look at this equation where m and k are some just constants and y is a function of t. How we can write this as a system and then write it in a normal form? So as a system we can write it as follows. So let's say x1 will be y and x2 will be, say, y prime. And then what do we have? We have that x2 is x1 prime, right? Because x1 is y, x2 is y prime, so x2 is x1 prime. And in this equation, what do we have? M x2 prime. x2 prime is exactly y double prime plus k x1 is 0. So instead of y, we write x1. So what do we get now? We get a system where x1 prime is x2, and x2 prime we can find from this equation here. We move this kx1 to the right and divide by m, so this is k over m x1. So we obtain this system where on the left side we have only derivatives and on the right side we have only functions. So the normal form of this system is when this bold vector x consists of two components, because we have only two functions here, x1 and x2, and the matrix A will be, so we look at the first equation. For x1 we have 0, right? So 0. For x2 we have coefficient 1. And in the second equation for x1 we have coefficient k over m. Sorry, should be of course minus, because we moved kx1 to the right with minus, and 0 here. So the normal form of this system, x prime is 0, 1 minus k over m 0 x. Okay, and in fact any linear equation, nth order linear equation, can be written in normal form. How this can be done? The same way we denote x1 to be y, x2 to be y prime, x3 to be y second derivative, and so on. And how many x will have overall? There will be xn. This will be x to the y to the derivative n minus first one. And after these notations, what do we have? We have that x1 prime, so on the left hand side we must have these things, right? x1 prime, this is y prime, which is exactly x2, right? x2 prime, y double prime, which is x3. x3 prime, this is y to the third derivative of y, which is x4, and so on. So in fact, let me write here xn minus 1 prime, which will be xn, right, by the same pattern here. And what is xn prime? This is the derivative of xn, so this is yn, and this yn can be found from the equation. So this is yn, which can be found from the equation. This is minus 1 over an, and everything which is, we move there, a0y plus a1 y prime plus so on until an minus 1 yn minus 1. And now we replace all this y prime and so on with our notation. So y is x1, a0 x1 plus a1 x2 plus so on plus an minus 1 xn. So you see, we indeed obtain a system where on the left hand side we have only derivatives and only functions on the right hand side. This is a normal form of this linear differential equation. The normal form also can be obtained not just for differential equations, but also for the systems with higher derivatives. For example, let's look at this system where we have second derivative of x and second derivative of y. So what can we do here? Again, we introduce x1, let's say this is x, x2, let's say x prime, x3, let's say y, and x4, let's say y prime. And let's see, what do we have? x1 prime, x2 prime, x3 prime, x4 prime. We need to write these things in this form, in normal form. So x1 prime, this is exactly x prime. So this is x2. x2 prime, this is x double prime, and x double prime can be found from the first equation. This is x double prime, which is, from the first equation, this is 2y minus 6x over 2, or this is y minus 3x. And now we substitute by what we have. Y is x3 and x is x1, so this is x3 minus 3x1. And x3 prime, this is y prime, which is x4. And x4 prime, again, this is y second derivative, which can be found from the second equation here. This is 2x minus 2y, or x is x1, so 2x1, y is x3, so minus 2x3. So overall, what do we have? This is x prime, this is matrix. Let's write the coefficients. In the first equation we have 1 only in front of x2, so 0, 1, 0, 0. In the second coefficient, in the second equation, coefficient of x1 is minus 3, of x2 no coefficient, x3 is 1, x4 again no coefficients. For the third line we look at the third equation, and only for x4 we have coefficient 1. And for the fourth line we look at the fourth equation, we have 2 coefficient of x1, for x2 no coefficients, for x3 minus 2, for x4 no coefficients. So we get this normal form of this system.